I'm gonna go ahead and record so I don't forget, because I forgot last time or something happened and it didn't work. You're on TV. Let me share this. Got it. No, yeah, share content. Broadcast. Okay, that worked. We got like a ton to cover, so I'm just going to go ahead and get started. And if people are still coming in, that's totally fine. Okay, we have, since we only have 2 recitations for the Monday recitation for this whole homework, we've got a lot to kind of cram in today. There's 3 recitations for the, what day is today's? Wednesday, right? So you can spread it out over a little bit more time. And if you need to, by all means, go to both recitations or whatever, or email me with a question or stay after and ask a question. But I want to get through everything on the homework, which means we have 4 more questions to get through today. So I'm going to go relatively quickly. My email is right there at the top of the screen. Please send me an email if you have a question about something you want to go over, your MATLAB code specifically or whatever. Do you guys know where to find the recitation resources? Question mark. Do people know where to find that on Blackboard?
Yes.
Yeah. Okay. It is in Blackboard. It's in learning modules, and I think it says recitation examples. And then there's a folder for Trey and a folder for me. I forgot to record last time. Sorry about that. So that's not in there, but the PDF is in there, and this PDF and the recording will be in there. I'm going to try to put that up tonight because I think there's going to be some useful stuff in here for you guys to finish the homework with. Okay. Without further ado, I'm going to go ahead and get started. So let's start in on homework problem 6, which is a damped oscillator. For problem 6, a hint is I want you to assume that A is not 0. You have to find A and you have to find phi. And if you assume that A isn't 0, which sort of makes sense, right? A is sort of like the amplitude of this oscillation, right? And if it's 0, then it's not moving, nothing's happening. So it makes sense that it's not 0, but bear that in mind as you solve it, okay? And let me show you what I mean by that real quick. So we're actually going to work through kind of the first part of this question together. So here's question 6. We've got a 2.5 kilogram mass. It's attached to a parallel combination spring with a stiffness of 3,000 newtons per meter. And a damper with a mechanical resistance of 5 Newton seconds per meter. While at rest at the equilibrium position, the mass is suddenly given an initial velocity of 3 meters per second. We want to know the relaxation time, which we called tau in lecture, omega d, which is the natural frequency of a damped oscillator, the amplitude and the phase phi of the oscillation. I have a practice problem that we'll talk about a little bit more, but I want to do the first part of the actual problem so I can kind of show you what I meant by that hint. Okay, so we know the equation of motion here, right? We didn't have to do any sneaky differential equations because we saw this exact same thing in lecture, right? The system looks like, I think I have it here. Oh, maybe I don't. The system looks like this, I believe, if we draw it out. We've got a spring, okay? We've got a damper, so like that, right? And we've got a mass. So I believe that's our system, and we've dealt with this system before, right? And in class, we figured out an equation for motion, and even we figured out an equation for velocity. We took the derivative of that. So we know it, right? And it is x of t equals a cosine omega dt plus phi times e to the negative beta t, right? So we're going to start from that place, okay? And you're going to start from that place when you do the homework problem. And I'm going to use some initial conditions to figure out what A and phi are. Figuring out what omega D is and what beta is, that's actually pretty trivial, right? We have equations for that. I'll give you those here in a second, but they look like this, right? We can just punch those numbers in. We can put those into MATLAB or whatever, and it will just spit those numbers out for us. What's sort of tricky is figuring out A and phi. So what I'm going to do is I want to write an equation for the equation of motion at t equals 0. So what is x of t? What is x? What's the displacement or the position at t equals 0? Does anybody know that? Reading the problem. Where does this thing start at?
0.
Yeah, totally, right? X of 0 is 0. So I'm going to say 0 equals a cosine omega d t plus phi. I could figure out omega d and I could figure out beta and have those in here, but it's not going to really matter. So I'm not going to do that right now. Beta t. Okay, so if I consider beta and omega d as constants, because I can figure those out, I'm left with two unknowns here, right? But let's simplify this a little bit. T was 0, right? So this is going to go to 0. T is 0, so this is going to go to 1. Everybody okay with that, right? E to the 0 is 1. So that gives me 0 equals a cosine phi. So this is where that hint comes in. A is not 0. So that tells you a little bit about that. Because otherwise, this equation is kind of like ambiguous. It doesn't give us a whole lot of information if I don't know that about A. Okay, I don't want to go any further with this question, right? But I wanted to give you that because I think it might save you if you get bogged down in this question. Okay. Okay, I'm going to keep going. Like I said, we got a ton to do here. So this practice problem, which is really the same question, except for instead of giving this some instantaneous velocity, we're going to do it like we did in class, which is to displace that mass and let it kind of like snap back, right? We're going to pull it away from its equilibrium position and let it, let the spring pull it back to 0, x equals 0, and then see what happens. Does it oscillate? Does it just go like, exponentially to 0 and stop? What happens, right? I made you this table, and I hope this is useful. Like I said, this is going to be posted. You're welcome to copy it down. You have all of it in notes, just maybe might be slightly better organized here. But I hope that this will get you everywhere you need to go, right? Omega naught, we just have an equation. There's nothing to that, right? Beta, same thing. Tau, same thing. Omega D, same thing, right? You're not asked for Q in this question, but I threw it in here for completeness, equality factor, right? And then how do you determine whether it's underdamped, overdamped, or critically damped? I have all those conditions here for you. And I have a little graph I made so you can kind of remember what it looks like when those conditions are true, right? Remember, if it's underdamped, it's oscillatory, right? Like if in this case, I pulled my mass back to x equals 2, it looks like, right? And if I let that mass go, it's going to overshoot the equilibrium position. And then it's going to come back and overcorrect, and it's going to do that for a little while before it runs out of energy, right? That's underdamped, okay? When it's overdamped, it's so damped that it takes a while to kind of like slide back to x equals 0. That's the blue line there. And when it's critically damped, it's just getting to x equals 0 as fast as it's possible to get there, okay? So I hope that's useful. I'm not going to run this one. I might show it to you in MATLAB here in a little bit, just to kind of like reinforce this idea that it's super possible to just write a program in MATLAB to do your homework for you. And I'll show you what mine looks like for this, in case you want to give that a shot. Like I said, I like to do it on paper and in MATLAB, and then kind of compare the answers and make sure I'm on the right track. Also, this is also something I'm repeating, but when you do it in MATLAB, it's generic, it works for any question that looks like this. You just change those constants. All right. Any questions on that for right now?
Nope.
Okay, I guess I'll just say, I'll give you like a generic recipe for this too. the way this is gonna work, any question like this, you're gonna run all the stuff that's really true. Well, start by writing your variables, right? But then the ones that you're given. And then you're gonna you're gonna crunch the numbers on all the trivial stuff, right? So find omega naught and beta and whatever else you need, right? And then write the equation of motion for position, right? And then take the derivative of that, or if you already have it, like in this case we do, I wrote it down for you here. There's the equation for velocity. That's just the derivative of the one above it with respect to time. Write those down and use your initial conditions to find A and phi, right? That's not specific to my practice one or the one on your homework. That'll work for these problems generally. Okay. I'm going to leave that there for right now. Like I said, we might come back to it in MATLAB, but I don't really want to switch over. All right. Okay. What do we got next? Oh, I guess we are going to MATLAB next. I'm just going to do these in order. I expect that probably the most useful stuff for you guys is the MATLAB stuff and then the equivalent circuits. Figuring, tell me if I'm wrong, but I'm figuring those would be the most useful maybe to spend more time on. I'm going to stop sharing my screen here and I'm going to move over to the computer. How do you do that? Zoom meeting, right? No, yeah, sorry. Okay. So let me share on here and let's look at some MATLAB. Okay, I'm actually going to come back to this for a second. So what you're asked to do, let's actually jump up and read the problem statement here. We've got a 0.3 kilogram mass connected to a spring stiffness of 5,000 newtons per meter and a damper with a mechanical resistance of 0.9 kilograms. We want to plot, it looks like the magnitude and the magnitude response graph and the angle, right? Of the impedance, pretty sure. Phase of the, yeah, magnitude and phase of the impedance. Then we've got some other stuff we need to do. I wrote you a recipe for this. I was thinking about what would be the most useful if you were trying to figure this out later. And this is what I came up with, okay? So there's kind of two parts to this question. One, you have to know like sort of the sciencey stuff, right? What physically is happening, right? So what equations do I need to use and so on and so forth. And the second part is how to do the MATLAB. And I wrote you a MATLAB recipe for this, okay? And this is it. It tells you step by step what you should do. Define the variables for your given quantities, use log space to create your frequency array in hertz and translate that into omega. And so on and so forth. I'm not going to read through all of that, but this will be available for you. And I really hope that that will be super useful when you're sitting down to do it. But let's take a look at what it looks like in my implementation here, okay? So problem 7, right? Okay. So what I did, I didn't want to show you exactly what this looks like in terms of like I just didn't want to give away the answer. So I changed some constants here and it's going to look awful similar, but I think that's going to be okay. All right, so here's what we're going to do. We're going to write down our given quantities. This is really step one, no matter what you're doing, right? We know our mass, we know our K value, we know our R value, those are given, right? So I'm just going to assign those to some variables. Doesn't matter what you name those. I find it helpful. I mean, obviously I went a little bit above and beyond with the comments because I wanted you guys to be able to read it, but it's helpful generally, even if it's just code for you to comment it pretty well. Then I'm going to create my frequency array. All right. I'm going to do that with log space. I want to go from 20 hertz to 20 kilohertz. And I'll do that in 1,000 points, right? This is really just the resolution of your graph. It doesn't matter what you put here, though it's not going to work very well if that number is too small, and it's going to take a long time if that number is too large. Okay, that's just resolution. The next thing I'm going to do is I need to make an array that's in radians per second. I just want the omega version of this. So we know that omega equals 2 pi times frequency. So I'm just going to multiply that whole array, or every element in that array, by 2 pi. Okay, it's smart enough to know because 2 and pi are not arrays, it knows that I want to do an element-wise multiplication here, but we'll get to when you need to be specific about that. So what I've got now, up to this point, let's just run this section. What I've got now is an F array, right? Which is just, these frequencies starting at 20 and 1,000 points. And I've got an omega array right here, which I just call W because typing omega, I think you can do it, but it's a hassle, right? It's just each element multiplied by 2 pi. And that's, those 1,000 points, but just in radians per second, okay? All right. Okay, let's compute my needed quantities. So I want to know the mechanical reactance, okay? Because that's going to help me get my impedance, all right? I'm not going to hover too long on this because I might be giving away a lot, but those are the things I want to know, okay? I am going to use magnitude and angle, right? Or sorry, absolute value, which is ABS, and angle, and this is in your recipe. But I'm going to use those to find the magnitude and the angle of my impedance. Okay, these functions are really helpful. And then I got to create my plot. You're going to use subplot. You're going to use a log-log plot and a semi-log plot. This is all stuff you can really figure out just by using the help pages, the MATLAB help pages. Okay. And we're going to end up with something that kind of looks like this. So this is for a different set of values, but this is generally speaking what we kind of want to see, right? I've got impedance magnitude here, impedance angle here. They are subplots in the same figure, and we have logarithmic axes where we need them. Okay. Questions about that portion? That's sort of the first half of 7. Anything I did that didn't make sense? Having a little trouble kind of like figuring out how to present this to you in a way where it's not just like, these are the answers to your homework questions. Okay. If you come up with questions, let me know. I really do think that if you follow that recipe, it'll help. Okay. And I will be available if you're like, there's this one thing that won't work on my MATLAB. Just send me an email and figure it out. We can do a Zoom. Okay. Okay. Here's the second part, and the second part looks kind of the same. I'm putting all my quantities in here first. I'm assigning them to variables. But there is this one trick where I have put all of my resistance values, because you're given multiple resistance values. I put those in an array because I'm going to use a for loop to iterate through those. Okay, so those are in that array. We've got our frequency array right here. Does this one not use omega? Oh, I think I'm missing my omega. Oh no, there we go. Yeah, anyways. So there's my omega array, just like last time. I'm computing my reactance just like last time. This dot right here is important, right? This dot tells MATLAB, I don't want to do matrix multiplication here, right? I want to do element-wise multiplication. I want to do like element 1 times element 1 in my 2 arrays. I don't want to do matrix multiplication here, or division in this case, right? This is going to be important. Lots of times when you fail to include this, it'll give you a warning anyway, and it'll say that array is way too big. It's not going to work, right? But be aware of that. If you're telling MATLAB to multiply every single element in your array by a constant, or you want to multiply or divide element 1 by element 1 and element 2 by element 2, right? Then you do need this dot. It's not just going to be the regular slash or the regular multiplication sign. So now I'm using this for loop to iterate through those R values. If this is something you're unfamiliar with, you can do a little bit of Googling, or you can just look up MATLAB for loop, find the syntax. But I'm going to do my calculations based on those equations that I gave you. in terms of how to find velocity and how to find velocity and how to find impedance. I'm going to plot those, and I'm going to end up with something that looks like this. Okay. Again, different numbers, but kind of the general idea of where we want to end up. Okay. Questions?
About the way you did this. So, I mean, ultimately I managed to do this, but when I first tried using for loop, I had trouble having them being plotted in one single plot.
I know what you're talking about, and that's right here, I think, right? Hold on says, don't create a new figure when I tell you to plot again. Just plot on the same axes as we just did, right? That might save your bacon right there. Does that answer your question?
No, I also used hold on.
And it didn't work? So, it just kept making new figures?
Yeah, like it would never do what the instructions says. So I ended up have to, just, like plot x comma y1 comma x comma y2, yada yada.
Yeah, and to be clear, that's obviously totally fine. It doesn't matter how ugly your code is. You know what I mean? Like, if it does it, it does it. I would suggest that it's probably maybe placement of where you have your setting hold to on.
Yeah, it seems like
if you look at mine, I mean, it's definitely doing it, right? And then I'm assigning all this, like making it pretty and making the axes what I want. That's all happening below. That only needs to happen once. But this is making new ones every time. So if you want to fool with it, I suspect it's somewhere with where you're setting hold to on. That help? Yeah. Yeah. I mean, it sounds like you went about it the right way. And that's a really good point. Just that, like, don't if it makes it more complicated for you to use a for loop, you just want to do it 4 times, do it 4 times. It doesn't matter, right? So you can figure out how to get it on the same axis. And this is going to come into play there as well, right? Cool. Other questions? Should we jump over maybe to what these directions look like? Jesus, I have too much stuff open. In case you have questions about that. So I gave you the name of these functions in case you didn't know that. I mentioned using element-wise multiplication and division where you need to do so. I think that'll get you there. I'm confident. Well, we'll see, but I'm confident for right now. Okay. Okay. I'm going to leave that, but we can always come back. You got questions? Okay. All right. There's nothing in the chat right now, is there? I'm not looking in the chat. Get to the chat. If there's something in the chat, will somebody yell at me? Okay, let's jump to problem 8. Problem 8's kind of fun, actually. And I guess we don't need to do this on, we can do that right here too. Okay, so if you haven't looked at it in a while or haven't looked at it at all, looked at it at all. Question 8 is about plate reverbs, right? And if you're unfamiliar with this concept, the basic idea is you have this big steel plate. I think they're almost always steel. And you have a driver, which is just a speaker with kind of a cone cut off, kind of glued to it in the middle. And then you have a pickup somewhere on it, right? And it's certainly like rich cousin to the spring reverb, right? Spring reverb is really the same concept. These are generally much more expensive and tend to sound at least smoother, if not better. I was going to show you, like, so the most famous of all plate reverbs is the EMT 140, which made, I think EMT is either a German or a Swiss company. This came out in like 1957 or something. And if you were of a mind to buy one, you could pick one up for $2,200, but you have to collect it in person in United Kingdom. They're pretty neat. One famous, I mean, they're used on about a bazillion recordings, but one really famous application that I can think of is they were used by Rudy Van Gelder to record those super famous Blue Note sessions in the 50s and 60s. That reverb was a plate reverb like this. So anyways, it's a big old steel plate. They're massive. I don't know, like 6 foot by 4 foot, maybe something in that area. And it's like suspended by, not like springs, but suspended by something. Okay, anyways, that's a digression. Let's talk about what the question is. And the question here is, mechanical systems have been used to create reverberation effects by recording engineers since the early days of the industry. These systems have similar behavior to mass spring damper systems discussed in class. Rigid materials like plates have their own intrinsic stiffnesses and are damped by surrounding air as well as their own internal friction. For example, plate reverb, see below, consists of a large thin metal plate suspended on a frame by springs. A force actuator is placed in the middle of the plate, and a piezoelectric pickup is placed in one of the corners of the plate. When an audio signal is applied to the force actuator, vibrations are induced in the plate and sensed by the pickup. Okay, this is the force actuator. There's your piezo pickup. I don't know if you guys can see my mouse, but I think you said you could last time. In a few sentences, describe why this setup adds reverberation effect. And then the next question is, what's going to happen if we make that thing out of styrofoam instead? So let's talk about how that works. So we create an acoustic, so we're going to make an analogy to a room. We create an acoustic signal in a room, clapping, say, okay? What happens to the signal in that room? When you all AME folks, tell me what happens if I clap in a room. What happens to that signal?
The waves bounce off the walls.
Yeah, totally, right? Do they persist forever?
Little by little, they lose energy, so.
Yeah, totally, right? Okay, I like it. So they propagate across the room, right? We know that there's like a propagation speed of sound in air that's dependent on, I think like, definitely like elevation, but also like humidity and stuff like that, I think affects it. But anyways, that's not important. Okay, it propagates around the room, right? We have these vibrating air molecules that are the wave manifest. They bounce in corners and on the floor and on the ceiling, and they combine and with each other destructively and constructively. Okay, and eventually they dissipate. Cool. So bearing that in mind, what happens to a vibrational signal when it's input on the plate?
Does a similar thing.
Say it again, Corey.
There's a similar dynamics going on.
Yeah, totally, right? I mean, it propagates with some speed across the plate, right? And this vibration. Where does it lose energy, Corey, as it bounces around?
Yeah. I wrote down I don't know what I wrote down. Like the surrounding air and the internal friction.
Yeah, totally, right? Remember, it's like little springs and damper systems. It's important to understand what those dampers do. They convert vibrational energy to heat, right? They're taking away energy from the system and putting it somewhere else, right? So
right.
That's happening in the steel plate, right? It's also, we have it's got to displace air, which takes energy, right? Does it reflect, Corey? So anywhere
you mean does it? I said yes at the
Yeah.
thresholds of the plate.
Yeah, it bounces off. It bounces at the edges, right? Do you guys remember like that, like talking about that in physics with like light at a change in medium? This is another place I'm going to screw my physics up, and John Woo, you'll have to correct me, right? Like isn't that how it works with light, right? When you transition mediums, it like some is reflected and some goes through.
Mm-hmm.
Yeah, same deal, right? Okay, so we've got something that looks an awful lot like what happens in a room, right? And I think we sort of like know or understand what happens in a room, so that's pretty good. What happens to the signal in the room when there is a lot of acoustic damping in the room? So think like I don't know, a vocal booth, right? If you're an audio nerd, right? like what happens to kind of the amplitude of those waves in a highly damped room with a bunch of foam in it compared to when you're in like a reverb chamber that's you know, made of concrete or made of tile or something.
The room sounds a little dry, and that the acoustical sounds will be the reverb would be short, very
Yeah.
short tails.
Absolutely. Yeah. A shorter reverb. And that's what we mean by dry, right? Like it just doesn't persist for as long because more energy is being pulled out of it, you know, more quickly, right? Okay. Next question. Does styrofoam have more or less damping than steel? Think about what happens if you were to flick your fingernail against a steel plate versus styrofoam, or hit it with a mallet or whatever. Which one has more damping?
Has more damping.
Which one does?
The styrofoam.
Totally, right? I wanted to be clear on that because that could be kind of counterintuitive, right? Obviously, like the steel is heavier. It's probably going to take more force to bend it, right? It might have a higher spring constant, K, right? But it has less damping, right? It will vibrate on its own, right? In a way that styrofoam won't. I think that should be enough information to really write a good answer to this. Anybody want anything, like want to talk any more of it through? Keep energy in mind when you're writing your answer. I think that may be the most like sort of straightforward way to explain it. Okay, I'm leaving it there. We're cruising like pretty quickly, so we may well get to a point where we could just take individual questions if you want to do like a more office hours-y thing. And I'm also happy to stay longer. Oh, let's do, okay, so here we are. We're at the hard part, right? This, I think, is what's going to throw everybody for a loop. And I made another chart for you guys. Again, this is stuff you have from class, or most of it is anyways. It maybe presented here in a way that's, you know, it's just another way to access it, I guess. I'm going to stop sharing on here and switch to my iPad so I can draw. Give me 1 second. Okay. Is it working? Yeah, it's working. Okay, so here's a table of quantities that are important in spring systems and their analogous electrical quantity. Okay, position is charge, force is voltage, velocity is current. You will see those swap sometimes, but I don't think in this class. Okay, force is going to be voltage here, velocity is going to be current. All right. And then we've got these sort of like components, mechanical resistance, those dampers. Those are just like resistors. Masses are like inductors, and springs are like capacitors, but K and capacitance, or the spring constant and capacitance, are inversely proportional. So if you have a value K, you have for this the spring, you have a value 1 over K for the capacitor. Okay. Then I have these 2 columns for these, and they are what happens if you take K or R or M to an infinite value, right? Which is going to be the electrical equivalent of an open circuit. What does it become? So for a damper, right, it becomes a rigid bar, right? It can't be compressed or stretched. It's still a connection. It's still a link, okay? But it won't be stretched or compressed, okay? And it has 0 mass. They always have 0 mass in our world, okay? If M goes to infinity, we sort of know what that is, right? We get you get a singularity. We just made a black hole. Infinite, little physics joke for you. Infinite mass is fixed in position, okay? It can't be moved. Think about it as being glued to the page, right? It's stuck there. And then what about the spring? Same deal actually as the the damper, it's a rigid bar, can't be compressed or stretched, okay? I added this, which may or may not be useful to you. Please ignore it if it isn't. But what happens if you take these values to 0, okay? For the resistance, it's like there's no connection at all. It's just deleted. For the mass, it's no mass. There's still a connection, but it doesn't require any force to move. It's infinitely light. And for the spring, there's no connection. It's just deleted. And then I gave you these as a guide to help you solve these kind of questions. So if two components share the same voltage, they are in parallel, right? I don't know how long it's been for you guys, but you remember if I have some voltage V here, right? And I have, I don't know why it's square, and I have two resistors that are in parallel, okay? They have the same voltage across them, right? It's V over both of those, okay? So if I have two components that share the same force, they're in parallel. Do they share the same velocity / displacement, which is like current? It's kind of easier to think in terms of displacement, which is actually like charge rather than velocity, or at least it is for me, because you can kind of imagine that. You don't have to take the derivative, the time derivative of the displacement, right? But they're going to be the same, and it's going to get you the same result in this sort of thought experiment. So if they have the same displacement, right, that means they have the same current and they are in series, right? What happens if one of them goes to infinity? Well, if the other one can't move / compress / expand, right, meaning it can't have any displacement, right, then they're in series, right? Because that's what happens when if I have a resistor in series with another resistor, and the first resistor goes to infinite resistance, right, the other one doesn't get any current, right? And that's the analogy here. So lots to keep track of in your head. What happens if one of them goes to 0? If the other one can't move, compress, expand, they're in parallel. And what I mean by that is this analogy, right? If I draw my voltage source, draw it circular. Oh, it's plus and V. Hold on. If I draw my voltage source like this, and I have two resistors in parallel, right? And one of those resistors goes to 0, it's a short circuit, right? Then the current here is 0, okay? And that's what that last analogy is, okay? That's like just, I think, legitimately too much to wrap your head around, just like hearing it said that way. So let's do a practice one. Okay, I'm going to draw my voltage source first. I keep drawing this over and over again. Okay, so there's my voltage source. We'll call it F. Okay, that's the force over there on the right-hand side. Let's talk about M2. And what I want to talk about, or the way I want to approach this is I want to know, I think the most useful one in my head of all those 4 questions to ask myself is, what happens if that goes to infinity? What if that thing gets glued to the page? How does that affect all the other components? Okay, so if I send that mass to infinity, it becomes a black hole, it can't move, right? Can any of those other components move? Imagine M2, did I say M1? M2 here is nailed to the page, right? If you put force on M2, are any of those other components going to be able to compress or expand or move generally?
No, it'll be same as if M2 became a wall and you're just tugging on a wall, so nothing happens.
1000%, right? So that said, is M2 in series or in parallel with the rest of those things?
It'd be in series.
Yeah, absolutely, right? Okay, so we got the first part of our drawing. And what is M again? Anybody remind me? What component does M go to?
Inductor.
It's an inductor, indeed, which conveniently just looks like a spring, which is like the most awful thing, like in terms of being confused by something already confusing. So let's give that a value. Let's call that M2. All right, let's figure out some more stuff here. So I guess I want to know a little bit about, what do I want to know about next? I want to know, about M1. I want to know about M1. If I, again, if I nail M1 to the page, is there anything that can still move kind of besides M2? M2, no, sorry, I don't think M2 can't move. Could any of those other ones move if M1 can't move?
My intuition here says that if any one of these elements goes to infinity, the whole system can't move.
Oh, I like that intuition. That would mean they're all in what, Corey?
Series, but I don't know if that's right. I don't know.
Let's walk it through. This stuff is legitimately confusing, and luckily this one is like more confusing than any of the ones you're actually asked to answer. But could I, for now, can I add this? And this is kind of a weird way to do it, but could I add M1 down here? I'm going to add M1 down here because I think that's going to be in series with this other stuff. Right now, I can definitely see, I mean, I hope you guys can see it too, but if M1 is stuck there, nothing else can move, right? Because those connections are rigid also, right? And I guess that's important to realize, but like this point here, that's also rigid, right? So if it can't move, if M1's stuck in place, none of the other stuff can move either. What about, let's talk about R1. If R1 is stuck, right? It can't go, it can't compress or expand. Could M1 move?
No.
No, it couldn't. But let's talk about K and R2. Could K and R2 still compress if R1 was rigid?
Yes. No, wait, I'm sorry.
It
No.
couldn't, right? If R1's stuck, that whole side is stuck, right? That whole side meaning R1 and M1, right? So that's all stuck together, right? Which means the other side can't do anything because this side can't compress, right? So I kind of like R1 right here, okay? Because I think if R1 goes open circuit, right? Then there's nothing then I don't think anything else can move, right? I think that's in series with everything. Let's talk about R2, and we'll come back and do like a sanity check here. But let's talk about R2. Yeah, go ahead.
Do we suppose that the string, like the strings connecting those components, like we assume that they are tightly like,
yeah, that's
like they cannot move?
That's a great question. Yeah, let's not even consider them
that's the
string.
thing confused me.
Yeah, let's not even consider them string. Let's consider them bars, metal bars, immovable and massless.
Oh, I see.
Yep, because that changes everything, right? Right,
Yeah.
But no, they can't compress, they can't expand. They're a rigid connection.
Okay, I think. Thank you.
Yeah, you're welcome. Okay, let's talk R2 and K. If R2 goes to infinity, can K still move?
Yes.
Yes. So they're in what?
Parallel.
Yeah. I'm going to go ahead and draw this out because I think we just solved it, but we're going to check and see if it makes sense. Oh, wait, I don't want that. I want R2 here. Okay. It's going to be R2. And I want K, which is a spring, which means it's a capacitor with a value of 1/K. Careful there, right? Right there. So let's do some checks right quick. So in our circuit, if R2 went to infinity, it became an open circuit, everything else could still get current, right? There could still be charge that flowed through every other component, right? If you got rid of this, right? If R2 was gone, right? Everything, it's the circuit doesn't stop working, right? So that's good, because if R2 goes to infinity up at the top, that doesn't stop anything else from moving. Everything else can still move, right? The same thing is true with K, right? If K goes completely rigid, everything else can still move because R2 will compress, right? And that works in our electrical analogy, because if this goes open circuit, right, everything still works fine. So they're looking like they work here. And then we sort of checked the other ones already. We said that if M2 goes to infinity, the spring system stops moving altogether, right? And if M2 goes to infinity here, right? If this goes open circuit, that stops everything from working. So that's right. Okay. And the same is going to be true for R1 and M1. And I even drew this earlier, and we can check against what I drew, and yeah, it's the same. It's not, I don't have any delusions that we got to like it being like super intuitive and you're like all set now. But hopefully with a little bit of thinking, and with this like sitting in front of you, right? Hopefully you'll be able to sort all those, all the questions from the homework out. Questions on this, or would you guys like to do another practice one, or what would be useful right now?
I have a question on this topic on the homework.
Yeah.
I just am having a hard time reading the third question, part C.
Yeah.
There's a circle in the
Ignore-
rigid bar that I don't know what that means.
Ignore that circle. Good question.
Oh.
But I don't think that circle means anything. And I'm not sure why it's there. But it in any case doesn't affect your answer. But that one is weird because that wall isn't there, which changes things. So just be aware of it being weird. Think about it. Yeah. Do you want to try one with no wall? Would that be helpful?
Definitely.
Okay, let's do that. Is it? Hopefully everybody is okay with that. Just draw one without a wall, but I'm going to draw a simple one without a wall. Or I don't know. Hopefully we'll be able to solve it. Okay, so I want to make sure I don't draw the same one from the homework. Okay, so those are all in series. What if we had like, okay, let me do this. So I'm going to draw it left to right. I'll really throw things off. So here's my F. Let's push that into, I don't know, a spring, right? And maybe then a mass. But that mass is going to be hanging off and going to nowhere, okay? But then let's also do, this could be unsolvable, just because I don't know what I'm doing here, just making stuff up, but let's do a wall here with a damper. Okay, and let's just call these K, M, and R. All right, so let's start with our voltage source here, plus minus, and it's going into, I mean, it looks like it's directly connected to a couple of things. If R goes to infinity, can you talk to me about that? What is that going to mean for those other two things? If R becomes just a bar, a steel bar, massless steel bar, what's the force going to do to those other two things?
Won't you still be able to move the other two things?
Anybody have anybody agree and or disagree?
I actually disagree because I think that the resistance was higher. It wouldn't be able to spring, be more elastic.
And I think I agree with that last one. And here's why. I think it has to do, maybe the confusion has to do with the fact that all my little lines, remember, those are steel bars too, right? If I'm pushing against this thing and this entire chunk is a rigid, immovable steel bar, I'm really just pushing against that wall, aren't I? And this thing can't compress. And don't get don't. It's so weird to do this, but like this isn't a hinge or anything. Like it can't like bend in. So I think if R goes to infinity, I don't think K or M could have any velocity regardless of the force, which means they couldn't have any current, which means I think it's in series. Let's draw that down like that. Okay. Okay. So that's R. What about if M goes to infinity? If we nail M to the page, can K and R, could those still move?
Yes.
Yeah, I think so too. And I think it's going to end up working like this. Bear with me. Let's see if this makes sense. So we said that, okay. We said that we're still going to be able to, yeah, I think it goes like this. Let's see, so that's K, so that'll be a C, 1 over K, okay. So does this fit our description? I kind of want to just draw it and test it. So in this case, right, if the R goes to infinity, then K and M can't move. If M goes to infinity, then there's still current. So if this one, if we cross this out, right, current can still get to those other two, right? They're all good, right? We just said that. What about if C goes to infinity, meaning that the spring becomes a rigid steel bar, right? Well, R can still compress, right? M can still move. So I think we're okay. Let me disagree with this solution. As confusing as this is, one thing that might be kind of nice about it is you can sort of test yourself, right? Draw the circuit, right? And eliminate things, right? And or use some of those other 3 bullet points and see if it helps get you there, right? And then erase it and redraw it if it doesn't work.
I just have a quick question.
Yeah, shoot.
So if the force was acting towards M, like on the opposite side, would you then be able to move M and K if R were rigid, since the force is going? Okay.
Yeah, that's a great question. And yeah, absolutely, right? Because if R goes rigid, right, at that point with F on the other side, then we really just have a wall, right, at the end of the spring, right? Sort of just like connected that wall to the end of the spring, and the mass can still move and the spring can still compress. Does that answer your question?
Okay. Yeah. Yes, it does. Thank you.
Yeah, if you guys get stuck on these or any of the other parts, like you're like, I looked at this for 15 minutes and like, I think it's right, but is it right? Send me an email, we'll work through it. Corey, how are you? Did that help at all, doing the one with no wall?
Yeah, I feel better. I don't know. I was thinking about it way too literally. Like if we were in space and I was putting force on this system.
Yeah.
Which I think is the wrong way to think about it.
Yeah, it's like they're so idealized, right? Like all the connections, it's kind of like how the connections in your schematic drawing are these perfect conductors, right? That don't lose any, that have 0 resistance. Like these connections are all these massless, perfectly rigid structures that can't bend. I don't know. I don't know if that analogy makes any sense or is helpful, but yeah, I hope again that like if you're looking at this, right, maybe like bullet point 3 doesn't help you, or it like feels ambiguous. Try bullet point 4, or you know, one of the first 2, and see if that maybe helps. And they're not like, they should all be true, right? If you're pretty sure from bullet point 1 that the 2 components you're concerned about are in series, check it against bullet point 2, and that should give you the same answer, right? Hopefully that helps. Okay. I think we went through everything. Since we have 5 minutes, I just want to show you really quickly what my MATLAB looks like for a question like problem 6, right? Just in case you want to do it in MATLAB, maybe this is helpful. I'm going to stop sharing here, and then as soon as I'm done with that, which is not going to take probably even that full 5 minutes, I can take individual questions. Anybody can hang out, whatever. So let me stop sharing here and jump over to sharing here. I can find out where to do that. Yeah. So this is just my MATLAB for question 6. It's a lot of, you know, it's diminishing returns again, maybe more work than it's worth. Just do it on a piece of paper or whatever. But I'm doing my given quantities all here. This is some made up numbers, right? It is the one that is written on the PDF I'm going to put up, but it's not the numbers from the homework. Compute my trivial quantities, right? I know omega naught equals square root k over m, beta equals blah, 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 tau equals blah, 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 omega d, and so on and so forth, right? That's all pretty straightforward. Don't worry about these assumptive values. That's something else. Now I'm going to solve for a and phi, and this is what solving looks like, or this is one way to approach it in MATLAB. I'm going to set up my equation of motion. I'm going to find, and I'm going to go ahead and plug in my values here for beta and omega d, because I know those, I calculated those. So those are in there. I'm going to take the first derivative of that, and we're going to have my equation for velocity here. Then I'm going to assign those to equations. These are like variables, right? It's just like this equals this. This is, I have a new variable called equation 1 for this whole equation. And that's what I need, and this is the syntax for it, to put it into something like this. So this is solving for a system of equations. You can look this up for MATLAB, but it's just to solve equation 1 and equation 2 for these two two variables, which I think are sims from up here. Yeah, they're both symbolic variables. And it's here it gave me a little, like a tiny little array, right? And that's because there's a square root in here. And so it was like, you know, it got to be 2 different values that were possibly the correct values, right? I am going to just choose the first element in those arrays, the top one, the top 2 here, okay? It doesn't actually matter. I'll show you that in a second. It's going to give you the same physical system, okay? And then I'm plotting it. You don't have to plot that for this question, but you know, when you plot it, it's like, well, my question said like I'm pulling this mass back to 0.2 and I'm letting it go. Does this look like what that should look like? And I would say, yeah, I think it does. That looks okay to me. I could check omega and see if that looked right. But yeah, it gives me that feedback. If I do change these to 2s, right, that just means that my A and my phi are now the bottom 2, right? Let me run this so you can see. It looks exactly the same. Doesn't make any difference. Okay. Questions on that at all? We've got 1 minute. I like doing it also because like it's just MATLAB practice. You know what I mean? Is that a question? Okay. Okay. If you feel good about the homework and you want to take off and do some of it or do something else, you are free to do so. Thank you so much. If you have questions, you are free to hang out, and you can share your screen with me or whatever. Okay. Okay. See you.
Thank you.
Yeah.
You're welcome. Howdy.
I actually want to share my screen.
Yeah, by all means, let me stop sharing.
Can you stop the recording too, Ben?